Logicians, as we turn to section 9b, we're now going to learn 4 new rules of inference that have to do specifically with quantifiers. These rules allow you to introduce quantifiers and to drop quantifiers out. Now, I could read through them here. I will. Universal instantiation, universal generalization, existential generalization, and existential instantiation. As you can see, they fall into pairs. There's instantiation rules and there's generalization rules. There's universal rules, there's existential rules, and they each have their own nuances. But before I go through the boring labor of talking through them, I want to skip to the end and explain to you why and how you're going to be using them in proofs, because I think the rules might be more meaningful to you if you see why you're going to need them. So let me do this. I'm going to skip to the end. Da, 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 da. Okay. Let's look at a kind of a proof that you might do with instantiation rules and generalization rules. You're going to be given a set of premises in predicate logic. They'll probably include some quantified premises. So for example, our first 2 premises here are quantified statements, and the conclusion is a quantified statement. Now, I want you to think along with me for a second about what these statements mean and the ways in which we're going to prove our conclusion. So the first statement says this: for all x, for everything that there is, if something is S, then that thing is also T. The second premise says for all X, for everything there is, if something is T, then it's P. Now, pause right there. Do you see a pattern here? Does this remind you even of any implication rules that you know? Some like patterns of thought? Hopefully it reminds you of hypothetical syllogism. Hopefully you look at that and you think, wait a second, doesn't that mean that if something is S, then it's got to be P too, right? Because everything that's S is T and everything that's T is P. So everything that's S is P. You would be correct. If you're thinking about hypothetical syllogism, you're on the right track. Now, our third premise says there's some specific item, A, and that names an individual thing, not just kind of a general variable, A, like atom. Atom is S. All right, now combine those thoughts. If I know that A is S, atom is S, and I've already seen that whatever's S has got to be P, then I know that atom's got to be P. Great, yeah. And then you look at the conclusion, which is that something is P. Well, yeah, of course, yeah. If A is P, then something is P, namely A. Great. You're on the right track. Now, in order to do this in a proof, you might think, well, yeah, first thing I'm going to do is apply hypothetical syllogism to premises 1 and 2. But friends, you can't do that. You can't apply your implication rules to quantified statements, or rather to these statement functions that are bound, that are governed by quantifiers. You can't just like drop inside this quantified zone and like, now I'm going to do some implication rules. It doesn't work that way. You're going to have to drop the quantifiers out, then do your work with your implication rules, and then bring quantifiers back in. And the rules that let you do that are these instantiation rules and generalization rules. Okay, so watch how this works. First step we want to do is we want to get rid of the universal quantifier in premise 1. I want to say, look, if all the x's that are S are also T, then that's got to hold true for this particular one, A. So if A is S, then A is T. The rule that lets you make that deduction, that lets you do that, is called universal instantiation. Then you're going to do the same rule and apply to premise 2 and say, okay, not only is it true that for anything it's T, it's P, specifically if A is T, then it's P. Great. Now you can apply implication rules to these non-quantified statement functions. So for example, you can do modus ponens on 3 and 4. So 3 says A is S. 4 says if A is S, then A is T. Well, you can conclude, therefore, that A is T in line 6. That's just with implication rules. Then you can do another application of modus ponens on 5 and 6. Look, if A is T, then A is P. We just said A is T, therefore A is P. Great. Now I've heard that A, some particular individual thing, atom, let's say, is P. Now I need to get to like the existential generalization that something is such that it is P. That's the conclusion I'm going for. And there's a rule. It's called existential generalization, which lets me do that. Now, this basic pattern that you're going to be using instantiation and generalization rules at the beginning and at the end of your proofs, and in the middle, you're going to be doing implication and replacement rules. That's the basic way it's going to go. All right. So here's your basic pattern. First, you're probably going to have to use these instantiation generalization rules. Then you're going to use your old implication and replacement rules to get unquantified statement functions. Then you're going to bring back in the quantifiers using these 4 rules, which we are about to learn now. Okay, let's go back to the beginning. So instantiation, what do I mean by that? When instantiation is applied to a quantified statement, the quantifier is removed. All the variables that were bound by that quantifier, that were within its domain, are going to get replaced by the same instantial letter. And our example was A. What's an instantial letter? Well, it's either a variable, X, Y, Z, that don't refer to anything in particular, or a constant, A through W, which do name specific individuals. And they're going to be introduced by either universal or existential instantiation rules. So let's start with universal instantiation rules. That drops out a quantifier. You can go from, for all X, if X is P, then X is L, to saying, if S, Shane in particular is P, then it is, Shane is L. Now, here's what you don't want to do. You can't keep the quantifier and then drop in an instantial letter. Don't do that. That's what happened in this first mistake here. Don't mix and match your instantial letters. Whatever you replace X with in the first part, it's got to be also wherever that X occurs. You can't say, well, now it's going to be R. Those are 2 different things. You can't do that. And you can't even do like name and variable, or, constant and variable. So you got to be consistent in your substitution. Now, here's your official version. With universal instantiation, the instantial letter can be either a variable like Y or a constant that names a specific individual like A. That's going to be different for each of these rules, but that's what you remember with instantiation. Universal generalization goes the opposite direction. So you got some unquantified statement function, like if Y is P, then Y is T. It lets you generalize and say, for all X, if X is P, then X is T. It just went in the opposite direction here. Now, again, you got to be consistent in your substitutions. You don't mix and match your X's and Y's. Whatever you substitute for Y in one spot's got to be for all of them. With universal generalization, you can only generalize to like a variable. Remember that. A few restrictions on universal generalization. These are boring, so I don't want to talk about them. I just want you to memorize them and remember them. Basically, they don't let you cheat and do super weird, crazy stuff with these rules. Existential generalization. Again, this lets you go from an unquantified statement function to an existentially quantified one. So if I've got Y as M, I can go to, there's some X such that X is M. Misapplications, again, if you get inconsistent with your variable, with your instantial letter substitutions, that's going to be a problem. So with existential generalization, you can generalize either from a statement about a constant A, some particular thing A, like Abraham is S, to saying something is such that it's X. Sorry, something is such that it's S. Or from a variable, some Y is S, therefore something is such that it is S. You can do either one of those. And then finally, we've got existential instantiation. And again, this lets you drop out the existential quantifier. So if you've got some X is such that it's B and it's K, you can name it and say C, you know, I'm trying to think of a C name. I'm blanking at Kathy, right? Kathy is B and Kathy is K. Now, there is an important restriction on existential instantiation. Okay. You can only, well, for one thing, you can only instantiate to an individual constant. You can't instantiate to a variable, right? So it's got to be A through W, naming a specific individual, not X, Y, or Z. That is the result of existential instantiation. Furthermore, there's rules on which individual constant names you can use. The existential name that you pick, in this case it was A, it can't be a name that appears in any previous line of the proof. And it can't be a name that appears in the conclusion which you're trying to prove. So if A appears anywhere previously in the proof, you can't use it. And if it's what you're trying to prove, it fits in what you're trying to prove, you can't use it either. That's cheating. Now, this leads me to give you a hint. When you've got a proof and the premises that you're given are going to require you to instantiate an existentially quantified statement and a universally quantified statement, you want to instantiate the existential one first, because you can use any name you want. And then you can, like you might want it to be A that you existentially quantified to. And then when you do the universal quantification, you can use A again because there's no restrictions on the constants you pick for universal instantiation. You can make them both about A. But if you instantiate the universal one first and make it A, then you can't use A for the existential instantiation. The order matters. So do the existential instantiation first and then the universal one. Take my word for it, it's going to help you along the way. All right, your mission is to memorize the rules, memorize the restrictions, and then doing some proofs. Oh, yeah. Oh, yeah.